Right. So I think we are live. I hope you guys from home can hear us. Welcome to the October event of Astronomy on Tap Jena. Apologies for the delay. There was a bit of technical issue with the streaming key. So yes, we are live. Excellent.
Right.
So I think twice. Excellent. So I would like to welcome today Professor Manel Perucho from the University of València. Did I pronounce it right?
We say Valencia, but
Valencia. I'm sorry.
For you. But, yeah, Valencia is Spanish. It's okay.
Okay, excellent.
It's okay. Don't worry.
So we will discuss today about extragalactic jets, simulations, and many things. Things that will move you a bit far away from Earth, way away in the far universe. And to start, cheers to all from home. We wish we were in a pub and maybe one day we can do this in person. But until then, so great. Before I start asking Manel very nice questions about his work, I would like to give a brief CV. But if you want to know more about his extended CV, you can find the description on the event page on YouTube, the one you are watching right now. So let me do my notes. Yes. Manel is currently the Vice Dean of the Faculty of Physics at the University of València, and also is a tenured Associate Professor at the Astronomy and Astrophysics Department in the Faculty of Physics. He studies astrophysical scenarios related to relativistic hydrodynamics, and he will explain to us what this is. For example, extragalactic jets from active galactic nuclei, and outflows in X-ray binary stars and gamma-ray binary stars. So he also participates in observational campaigns using radio interferometry techniques, like the Very Long Baseline Interferometry, VLBI, and he collaborates with radio astronomers from different institutions. So, as I said, for a full CV, look at the description of today's event, and now we'll have a very nice discussion about what these simulations are and these astrophysical jets are. So Manel, I want to start not from the astrophysical jets, but a bit further back in time, from what inspired you to get into astrophysics, to study this phenomenon.
Yeah, well, first of all, thank you for the invitation, Eleni, and say hello to everybody watching us. I don't know how many people are interested in this, but I'm happy that if there is only one or two, it will be great to have people interested in science and in astrophysics in particular. Well, regarding your question, when I was a kid, I had an uncle who had not studied when he was young. He was a small-scale businessman, and but he liked science, and he had read Einstein's books about relativity and so on. And he kept telling me stories about travels in space-time and so on. And that, together with myself watching the stars and asking myself, why do they shine? I mean, what's the point that these whatevers are up there shining? What's the mechanism, right? So made it, but there is the last push was made by when I was the year before I started my degree studies, or 2 years before. I was in a history lecture, and I loved history. My best marks were in history always, and my history professor asked me, what do you want to do in the future? And I said, I want to be either physicist, astrophysicist, or historian. And he told me directly, study physics. So being a historian, that pushed me in that way. Anyway, so that's the origin of it.
Very nice. So you didn't want to be an astronaut like a lot of kids
No.
No. Oh.
I am quite a quiet person. Adventure is too much for me sometimes. So, and that's too much of an adventure. Okay. I have dreamed of traveling in space, but being up there already, no escape time or no landing, which is the worst of it. So I'm scared about that.
Actually, that's a very good idea. They should find a way to do that. Yes.
For the transportation.
I would go for that also. So you told us that you didn't tell us about your studies. So.
Well, I studied physics at the University of València, and then but here there was not much of astrophysics, and I had the clear idea of studying astrophysics. And in my fourth year, I went as an Erasmus student to Leeds University, and they told me, if you take all the astrophysics lectures, we won't convalidate you when you're back. And I said, I don't care. I mean, I want to do astrophysics. And I started taking lots of astrophysics courses there. Finally, I was lucky and I got most of it convalidated in a funny way. You know how these things go. I mean, electromagnetic radiation in astrophysics, for whatever, anything half related to it. But I mean, the people who are taking care of the mobility of students are very understanding. So nice. So to say, and then I came back and I studied after my degree. I studied the PhD courses here in the University of València too, and there I specialized in astrophysics with some theoretical physics, but mainly astrophysics. Yeah, with very good professors, by the way. I learned a lot those years. Yeah. Excellent.
And have you traveled the world? During your studies?
In conferences, yes, a lot. I mean, I have been to places where I could never have been to, like Alaska, for instance, to a conference, or or Japan, which it's a place I love, or Greece, which is a beautiful place. And I have lived in Germany for 4 years and a half. We lived in Bonn while during my postdoc. And that was a very great time. And actually, my daughter was born there, and we're very, very deeply in touch with Germany nowadays still. So.
Yes, Bonn unites us somehow. We all been through Bonn at some point. Yes. Absolutely, it's a very nice place. And hello to Bonn from Jena. Yeah.
Jena is. Yeah, I was to Jena too. For a weekend. It's a nice place too.
It's a very nice place. It's a student town.
Yeah.
Now that things started to open up, it's more lively, and I like it very much. And I was really looking forward to living in Jena, because I've heard it's very vibrant and things happen all the time. So I'm happy about that.
Excellent.
We should invite you one day to our institute, Gothenburg, to give a talk, and maybe we can discuss more about the astrophysical jets. Yeah. So we said what you do now. You have a lot of responsibilities at the University of València, and you also, in your free time, do research, right?
That's more or less it. Yes, I teach, which I love to. Also, I like teaching a lot, and I teach algebra and geometry in the first year of physics, and it's a very nice subject to teach because it brings lots of abstraction to the students' thoughts, and it, to some extent, is the time when they learn to get involved into this reasoning, mathematical reasoning, and so on. And you see how their eyes start shining when they understand things, and that's really nice from a teacher's perspective. And then I have lots of now paper load of, I mean, when you are in the administration team of a faculty, there's lots of meetings and paper load that you have to take along. And so hopefully I have collaborations that drag me to science. I have a PhD student who is doing very good, and I mean that keeps me in touch, keeps me alive. So
yes. No, that's good. It's always good to do science, because I feel you. Sometimes we feel like we're in a constant Zoom meeting and we're discussing about science, but we don't have time to do the science. Yeah. So yes, I sympathize. Okay, so you said you have students, you have a PhD student that does work, and this topic today was tailored a bit around astrophysical jets, because I had to have a theme for today's
you too, you too.
Because this is what I like. Yes, and also it's the theme, part of the theme for our quiz later. So the guys from home will play a quiz. So guys, you have to listen to this discussion now to maybe figure out what the answers are to the questions later. So I will start with a very simple one. What is an astrophysical jet?
The basic. Well, that's a question that a very good scientist at the Max Planck Institute used to ask me often. Richard Porcas, what is a jet? And I started thinking about it. Yes. Well, actually, I mean, in a few words, it's a channel filled with plasma, which is charged particles and magnetic field together, evolving together through whatever environment they have. We may talk about that later, and they are what we see, which is the radio jet. Actually, it's the result of the synchrotron radiation, which is the radiation that charged particles emit when they are embedded in magnetic fields. So this radiation is non-thermal. It's not like our bodies or the Earth or stars that are in thermal equilibrium and they emit thermal radiation at the temperature corresponding to their bodies, but it's the so-called non-thermal radiation, which is the one produced by accelerated charges, for instance, like in this case. So you have particles, and the particles are accelerated by the magnetic field, and they lose energy by emitting radiation. Mm-hmm. So what we see is particles and magnetic fields.
And we see this in the radio. We see this in the radio part of the electromagnetic.
This is in the, yeah. We see it in the radio, but there are other collateral emission, but that can be even as important as that in radio, which is the inverse Compton in high energies, which is the electrons that are emitting synchrotron are so energetic that when a light particle collides with one of them, can gain energy. So, well, the people outside physics may know that the physicists deal with particles as particles or waves, depending on their interest or what's better for them in the moment. But it's true that light has particle and wave properties. And when it's very energetic, it behaves more like a particle, and then there are collisions between these photons, these light particles, and the elementary particles, the electrons in the jet, and then these radio photons or optical photons from around the jet can be changed in energy to gamma rays or X-rays, so gain lots of energy, and then we see the jets also at high energies too. So there are plenty of processes out from which we get radiation. The main one, I'd say, it's synchrotron, which is the particles around the magnetic field lines, emitting radiation and losing energy by emitting radiation. Yeah.
So the structure of these jets is like a tube, right? Just to explain a bit.
Yeah, it's like a channel which is built by itself. So the first particles that are injected into the channel, we are talking about injection, were from maybe come later too. So imagine you have a water hose, right? So you are so the first drops of water are opening the way for the rest to come, right? So because the water develops through the air, the point is that it doesn't get much of resistance. So you see the water like propagating almost ballistically, if you want, like a bullet. But in the case of jets, they face their environments, and that costs some effort from them to open the way. So what happens is that the particles going through the channel reach the head of this channel before the channel manages to advance further. So they start these particles that cross the channel and get to the end. They start filling a region, and which we call radio low, which is the region where the particles going through the channel. So the water drops that go through this channel fill this region because they are finding. It's like when you throw the water to the earth, right? So you start the water starts spreading around the place where you are pointing the channel, right? So that's the idea. I hope this.
No, that's a very nice analogy with the water hose and the water falling. And I was wondering what type of objects in the universe have jets.
Well, jets are, this is a fashionable word to use in scientific papers. Jet in the introduction. Jets are serendipitous in the universe. They are everywhere, right? So they are very relevant for the evolution of their environment or even the galaxies. In order to have a jet, you need a compact object or basically an accreting object, an object that is accreting mass, accreting gas from the environment, and a magnetic field. The point is that the gas that goes onto the object brings its own magnetic field because the galaxies, the interstellar medium has, there is a magnetic field there. The origin of that is pretty much unknown. This cosmic magnetic field must be due to charges and rotation, but when and where, we don't know. So the point is that this gas carries its own magnetic field with it, and it arranges in disks because the most stable rotating shape for gas is a disk. Why? Because of collisions. If you have a cloud of gas rotating, collisions make it lose energy and it falls to a disk. So once you have a disk and it drags this magnetic field, and the disk is formed basically because there is an object in the center which is attracting this matter to itself, then you can form a jet. And this happens in forming stars, because stars, when they form, there is a part of the cloud from which they are born that collapses. It forms the core of the star, if you want, and then starts taking more gas from the rest of the cloud. There is a disk formed, and you can get a jet from that. Those are the so-called Herbig-Haro objects, out of which, I mean, there are beautiful images from the Hubble Space Telescope, because these are objects that we see in our own galaxy, and we have very good resolution for them. So this is one thing. Then there is another place where you can find, another scenario where you can find jets, which is in binary stars, in X-ray binary stars. So when you have a star that has, well, a binary star, so one star orbiting around the other, and one of them is massive enough to die in a supernova explosion or something similar, and you get, as a result, you get a compact object. Well, maybe it could also be a white dwarf because you have, I mean, the star could not die, not by explosion, but by losing the external layers, but still in the center you get a compact object. So a white dwarf, or from a supernova, you will get a neutron star or a black hole. Then one of the stars becomes such a compact object, but then the other is still a regular star, so to say. So it can happen that the regular star, the outer layers of this regular star, cross the region where the compact object gravity rules, and then this gas starts being attracted by the compact object. So it would be like stellar cannibalism, right? Yeah. In that case, this disk that would form around the compact object, plus the falling of this matter to the compact object with the magnetic field and so forth, would also generate a jet. Then we have active galaxies. Active galaxies are galaxies in which you have a supermassive black hole in the center, black holes with like hundreds of millions of masses that of our sun. which also accrete matter. And in this process, you can form jets. These are the ones in which I focus my studies more. This and the binary stars one. And then there is a last scenario, which is the massive stars that collapse and form and explode as supernovae. They can also generate very strong explosions, the gamma ray bursts, and they seem to be associated to the generation of jets. Very rapid and let's say temporary jets. They last for seconds maybe, but it's because during the collapse of the star there is a compact object formed in the center which accretes the matter around it, and then a very powerful jet is formed, and then you get a jet and an explosion, very bright in high energies, and then in the rest of the electromagnetic spectrum too. So those are the four main scenarios which are everywhere. I mean, forming stars, dying stars, binary stars, galaxies, so they're everywhere.
That's why we like jets, because they're everywhere.
Everywhere, yeah, absolutely.
Now you understand why I was biased about this topic today. But you said something that was very interesting, that the jets in this from the gamma ray bursts are very short timed, so they live for very little time. How long do the other jets live?
Well,
I mean, from the other
in the case of stars, I would say that it must be like hundreds, thousands of years. I don't really know the exact number in that case, but that would be around it. In the case of microquasars, you can have a jet as long. Microquasars are peculiar because you can have different stages of accretion and different stages of jet emission or not. So you can have something which is kind of periodical ejections, or you can have something more continuous depending on the system. Okay. But in that case, it takes as long as the companion star gives material to that star. So that can take, let's say, millions, some million years at most, something like that.
And what is the microquasar?
Sorry, I used the other word. It's an X-ray binary. Sorry, yeah, good point. The microquasar. I said microquasar when I should have said X-ray binary. So this is the system of the stellar cannibalism that I was mentioning before. So as long as you have a donor star, a star that gives its external layers to the compact object, you may have a jet, and that takes as long as the donor star lives. If it's a massive star, it will be less. If it's a low mass star, it can take millions of years. And then galactic nuclei, you can have that for hundreds of millions of years going on. However, jet ejection, we don't know this so far. But jet ejection can be, I don't know, from some million to some tens of millions, maybe in some galaxies, very powerful ones, in terms of brightness, right? So very not powerful jets. That's another thing. But galaxies that are active and have very long jets that have evolved for a long time, but very slowly because the jet power is not very large, but the galaxy is very bright. The point in that case, it can be hundreds of millions of years. So a fraction of the age of the universe. That's the point. So from some million to a fraction of the age of the universe. And
to remind the viewers that the universe is 13.7 billion.
It's billion American or Anglo-Saxon billions, which is 13.7 thousand million years, right? So
1,000 million, okay.
1,000 million, which is this is for us, for the Europeans.
Yes, I think also the Germans use that.
Also, sorry.
Yes, do they say
for the South European?
The billion, they say miljarden, and I always get confused.
Yes,
like,
that's true.
What is this miljarden they talk about? Yes, German language is very hard for my comprehension, unfortunately.
It's very nice.
It's a beautiful language, but a bit complicated.
Yes.
I find the universe less complicated than the German language.
No, come on.
Okay, I'm exaggerating.
Yes.
A little bit. Okay, so we talked about the jets, where they come from, the supermassive black holes. So we said in the center of galaxies, you have supermassive black holes. Do we have jets in every galaxy? And do we have a radio jet in our own galaxy?
About the first question, no. The answer is clear. No, there is not a jet in every galaxy, not that we can observe at least, because that's actually what differentiates active galaxies from non-active galaxies. Not the presence of the jet, but the fact that makes the jet happen. Because the point is that you need that the central black hole is accreting. And accreting at a good rate. So let's say that it swallows like some stellar masses per year. This means sometimes the mass of the sun per year, right? If the central black hole in the center of the galaxy is swallowing this amount of matter, then you have an active galaxy. And depending on how this accreting matter arranges on the one hand, and also on the rate at which it swallows the matter, then you may have a jet or not. The difference between having a jet or not, I'm saying it grossly. We don't know also. We are studying this actually. We are studying why some active galaxies do have jets and why some others do not. So why some galaxies are, some black holes in the center of galaxies are swallowing matter and others are not? Good question. The point is that we typically associate galactic activity to mergers. This is collisions between galaxies. This is also not completely clear, but there is a correlation between galactic activity and distorted morphologies of galaxies, which can be due to the collision between the galaxy that's, let's say, the active one and a minor one that collided with it, or I don't know, the size of the galaxies is irrelevant, but some distortion, and this brings gas from the other galaxy to the center of the active galaxy, and this gas is the one, this plasma that falls into the plasma is with magnetic field, right? So it's gas with magnetic field. So this plasma that falls onto the black hole is the one that it's making this galaxy being active, right? So that's what makes the difference. Our galaxy, okay, that's a controversial question. I don't have an answer. I think we don't have an answer for that. But there are hints of non-thermal emission. So there's something going on, and there's people who take this as a proof that there is some ejection, and that we don't see it because of a relativistic effect, which is the following. I'm sorry I have to explain this. Do I have time to explain this? Yes? Okay.
Absolutely. This is a very important point. Please.
All right. So
I will have a sip of my beer to understand this better.
Good. I'll do that later. So the point is that when I said in the beginning that particles, charged particles that are embedded in magnetic fields, they radiate, they emit radiation. If the velocity of the particle is small, this radiation is emitted isotropically. So the same amount of radiation is emitted in all directions. However, if the particle propagates close to the speed of light, there is a preferred direction, which is the direction of motion of the particle. So most of the radiated energy goes ahead in the direction of motion of the particle. Sorry, I have my cat wanting to enter. Okay.
Maybe she does not agree.
No, maybe not. I don't know. So the point is that if we are on the plane of the galaxy and we are orbiting around the black hole, and the gas which is falling onto the black hole is orbiting in the same plane, and the jet is ejected perpendicular to our line of sight, then we wouldn't see whatever is ejected close to the speed of light, because the radiation would be emitted perpendicular to our direction and not towards us, right? Also, you have to add lots of absorbing features on the way, whatever. Anyway, so the point is that these people say that maybe there is a jet because there are hints. And there is also these Fermi bubbles that some people claim that have. The Fermi bubbles are like two lobes on the poles of the galactic plane, so perpendicular to the galactic plane, that show high energy emission in gamma rays. Actually, they were observed by Fermi. That's why they're called Fermi bubbles. And some people in the field claim that these bubbles are fed by a jet, by jets, two jets. So one in each direction. So the point is that there are these kind of evidences that could point towards, but we don't see anything from here. We don't see any jet. We don't see extended emission from the black hole. We don't see whatever we could associate to a jet. So there is controversy about that. My answer is I don't know, which is this is the typical answer you wouldn't hear in a radio program with lots of journalists, right? I don't know. Opinators.
If you had the journalists and the funding body, you would say yes. Yes, there is. Give us money, we will prove it.
That's another point. Yes.
Yeah. And so yes, you have a jet. And you have a counterjet.
Yeah.
Why?
Well, because of they don't necessarily have to be equal, but symmetry. The system is symmetric, right? You have a spherical object, and then you have a disk. So the system is symmetric, and then you would expect that a symmetric behavior would generate a symmetric situation on the poles of the rotation axis, right? So on the rotation axis, along both rotation axes. Well. The rotation axis, but there is one. So that's why, but they don't have to be the same. Actually, we actually published a paper like 1-2 years ago, I don't know, about Batschko et al. She's a German scientist. So she's working in the Max Planck Institute. So with people at the Max Planck Institute and at the University of Würzburg, we studied the ejection in a nearby active galactic nuclei, which is NGC 1052. Right? So that's the phone number if you want to check for anything. So we realized that these two jets that are emitted from the black hole at the center of this galaxy are basically on the plane of the sky. This means they are ejected perpendicular to our line of sight. So you should see whatever you see very symmetrical, and they are not exactly the same. They have differences, but this might be due to second order effects on the whatever is taking. If the disk is somehow a bit thick, you can have differences on both layers, and the magnetic field reaching the compact object from both sides is maybe different too. You may have like in the sun, you have solar flares, you have inhomogeneities in the solar magnetic field, so you can have also that so why not? You should have that, right?
Yes. Can you also have different environments on the top, let's say, and on the bottom?
Yeah. If the galaxy is a spiral galaxy, you have you have the spiral arms, and then you have a bulge in the center of the galaxy. So that bulge is not is thicker than the rest of the galaxy. But once the jet goes through this bulge, it will find the intergalactic medium, which should be more or less similar on both sides, unless there is a satellite galaxy or something. Inside the galaxy, inside the bulge, you should expect inhomogeneities because you have clouds, molecular clouds of gas here and there, but they are not ordered, right? So you can one jet may find a cloud and the other not, and so on. And this is in spiral galaxies which barely have jets. Some of them may have, but not in general. Jets usually appear in elliptical galaxies, which are by the way, these elliptical galaxies are in general. We think that they are generated by collisions between galaxies. So that's why the galaxies having jets usually have this morphology. So they are ellipses or spheroids of gas with stars and so on. And the jet takes lots of time to cross the galaxy because it has to cross the whole of it. And these are big ones because the gas is spread all around. And it's not only a small bulge and then you're out. You have to cross the whole galaxy, and the galaxy on one side and on the other, because of the same as I said just before, might be perfectly different. I mean, you might have lots of asymmetries. And now, how important, how relevant are these asymmetries? It depends on the jet power. If the jet is very powerful, it doesn't care very much. It just goes through, just bursts everything. If the jet is not so powerful, that may be very important. And you might have on the edges of being very powerful and not being very powerful. We know of galaxies that have radio jets, and they have different morphologies on both sides. So on one side, the jet went through very easily, apparently, and on the other side, it's kind of disrupted. And this means that it had a bad time, and it's the same source. So, and also we said that there are small scale asymmetries, but this is in the small scales, very close to the black hole. Once you are very far away, things are kind of integrated and wiped out by time, and they should be more or less symmetric, both jets at the large scales. And you see sources in which this is not the case. And that's why one of them is having a bad time, and it's on the limit of being destabilized and broken by. So it's like if your water channel is kind of some kid gets through, right? And then it's stopped. So yes. That's the idea. And on the other side, you have two of them, and there is one kid on one side and there is no kid on the other side. So.
Yes, very nice. Yes, we got the kid all wet now.
Yeah.
So,
but happy.
Okay, so this will bring me to my next section of questions, but before that, yes, please have some beer, and we'll play a game. We will play true or false. Okay, let me check my live chat. Hello, guys. Yes, we will take your questions at the end, please. Well, this is the kid that didn't get wet.
Hello.
This is my son.
Hello, nice to meet you.
We are live on Astronomy on Tap. Do you have a question?
Hello.
Hello. Bye-bye. Cheers. So guys, if you have questions, please add them to the chat. We will answer them after we finish. Sorry, let me find my questions.
I was told that I would lose my
questions. Ask me.
You will get the good ones.
Yeah. He can answer the difficult ones.
Okay. I was told I would lose my degree if I failed.
Probably I will lose my degree after this.
I will get into music if I lose my degree.
We all have a backup plan. I will do some painting. You can do some music. Other people dance.
There's always a way out.
Yeah, astronomers have many skills because we know how difficult this field is.
Just in case. Yeah.
Just in case. Right. So, question number one. Not question. It's a true or false. Okay. So the largest jets emanating from galaxies are about 100 times the size of our galaxy and are the largest single objects in the universe. True or false?
Well, single objects, we exclude clusters.
Clusters are a collection of objects.
Okay, good. Yes, by definition, you're right. 100 times. Okay, the galaxy is 40. Can I think?
Yes.
Can I make numbers?
Yes.
The galaxy is more or less 40 kiloparsecs across. 100 times would be 400 kiloparsecs. That's too much, I think. The size, I mean the diameter of the galaxy, you say?
Let me check what I said.
100 times the size of our galaxy, but the size is the diameter?
The size of our galaxy
is about 40
how much is it?
150,000 light years, in order to speak in light years.
I have these numbers in kiloparsecs if you're interested.
Yeah, no, 50 kiloparsecs more or less across. Yeah.
Yes.
But 100 times 50 kiloparsecs would be 500. Yes. No, yeah, true. True.
Yes, we have what we call giant
yes.
galaxies. Yes. they are they extend to huge distances beyond.
Well, this is about let's say 2-3 million light years across. Yes, these are typically these show up typically in dilute environments, because then they have an easy way to go that far.
Yeah. So they don't find a lot of resistance from the.
Exactly. Yeah.
There is no kid crossing them.
There is no kids. Yeah.
No.
It would be burned out anyway.
No kid crossing, no cat crossing.
Nothing. The cat, by the way, is somewhere.
I'm surprised the cat didn't join the discussion.
I think my daughter says he just went away again. He was saying, oh no, jets again. No.
I'm fed up with this.
Yeah.
I wrote so many papers this year. I can't
yeah.
Okay. So, second statement, true or false? We can only observe astrophysical jets at radio wavelengths.
We can only false.
You explained to us before.
Yeah, we can. As I said before, we can observe them all across the electromagnetic spectrum. The electrons they emit mainly in the electrons around these magnetic fields that form the jets. They are emitted basically in radio, but the tail of the emission can get even to optical or to X-rays sometimes in synchrotron, and then you have the contribution of these photons that are upscattered, let's say. So the photons that gain energy because of collisions with electrons, and then this we see it in gamma rays or X-rays too. So it's all over the electromagnetic spectrum.
Can we see it in the optical?
In the optical too. In the optical, we have synchrotron in the optical, right? because when there is inverse Compton, it goes directly to very high energy, so past the optical. But well, actually, the first jet observed was the discovery of jets was made by an optical astronomer at the time when there was only optical astronomy. In 1915, was an astronomer called Curtis. I don't recall the name now. Sorry. And he observed the jet in M87, which is one of the nearest active galaxies. He mentioned it in a paper and called it a curious straight ray. And how curious it was, yeah, indeed.
Yes.
Very curious.
And what a famous galaxy M87. Yes.
Fashionable.
Okay, so the third statement, true or false? Jets can travel faster than the speed of light.
False. That's false. Nothing travels faster than light.
Yes.
Cherenkov, particles that emit Cherenkov.
Okay. So I had in mind superluminar motion.
Apparently, yes, they can.
Apparently. What we observe,
yes. Yes, but they don't move. They don't propagate faster than the speed of light. We observe them propagating faster than the speed of light. This is another relativistic effect, and this is why we know there are two reasons why we know that jets in active galaxies are relativistic. One is the fact this collimation of radiation, because when an active galaxy with a jet has a jet pointing more or less to our line of sight, we see one jet, but we don't see the other. We see the jet, but we don't see the counterjet. And sometimes we see the effect of the counterjet. Once it is decelerated because of the collision with the ambient medium, the deceleration makes it bright at the so-called hotspots or lobes that I mentioned before. And this we see, but we don't see the jet. So this means that we see the jet coming towards us, but not the counterjet, because its radiation is being emitted in the other direction, and some alien civilization may be seeing it somewhere else. So we're missing that one, and that's one. And the second one is what the effect related to the question, which is that precisely the jets that point close to our line of sight, when we observe them in radio and we identify a feature of the jet that moves through the channel, along the channel, you can take the position and you measure how much it moved, and then you divide by time, you get the velocity, and this is larger than the speed of light. But this is relativity faking us, because it's a combination of this fast motion of the plasma and the small line of sight. It can be explained by geometry. It was explained by Martin Rees in the late 60s, I think, of the last century. And it's all about geometry and relativity. So one of the most terrible aspects of jets is that relativity fakes everything that you see, and you have to deconstruct it and go to the, deproject and then whatever, and it's everything a mess due to relativity. It's terrible, but it's also amazing. It's very nice.
Yeah, I know. I also deal with problems of jets being projected in the sky, in large objects, and how annoying this is. Yes, and I get comments on my research. Oh, did you deproject them? Okay, the audience does not understand this, but this is an inside joke.
That happened to me too, yes.
Yeah. And I'm like, yes, I wish. Okay, and this brings me to the next big topic, which is simulations. And because we explained what these amazing objects are that are the most important things in the universe, apparently.
Well, no, I don't know whether they're the most important, but they are very important. They are very important.
Yes, they're very important, and we love them. And that's why we study.
That's what makes them the most important.
But we don't only observe them. We don't only take observations with our telescopes. We also study them with models. We make models, and Manel is an expert on that. So I want you to give us a simple recipe of how to make a radio jet. And I know you have some videos to show us.
Yes. Yeah. Well, actually, there are two kinds of jet simulator, because jets. Let me explain this with an analogy. Imagine you want to simulate a water channel from a water hose, right? And that you have your water hose in Jena, and the water reaches Rio de Janeiro. So these are the different scales. And when you want to put that into a computer, that's terrible, because what should you focus on, the effect in Rio de Janeiro or on the region where it is forming, right? So you have to choose. And this depends basically on who your PhD supervisor was, because that actually. So there is simulators who run simulations to learn how jets are formed, right? So they focus on the base of the jet. So they have a compact object in the center, the supermassive black hole. They have a magnetized accretion disk, and they see how the jets are formed and so on. And in my case, what I do is to take a numerical box. I will explain what this is now, and inject the jet already formed, right? And what we can see is something like this. Let me share my screen. And how should I do this? I don't have the option to do that, do I? Here?
Oh my God, you should.
Okay, I don't have it.
Share screen. You don't have the option of share screen.
I see reactions, record. No, it's here. Sorry. My self being focused on the explanations. Can you see now the YouTube thing?
Yes.
Okay, this is a video I produced some months ago, and it's a jet traveling through the inner, let's say, 1,000 light years within the galaxy. So you see that there are clouds around that the jet has to cross. The jet is already there. You can see it. You can see it here. Let me open this. Okay. The jet is already here, because when I started this, so I take frames of each of the simulations, and the first one I took was with the jet already inside. So here you have, let's say, clouds which are cold, which host atomic hydrogen, and then you have in between them you have a hotter ambient medium, which is like ionized hydrogen. So electrons and protons go around them on their own, and then you inject this powerful thing at a small distance from the black hole. The black hole should be somewhere here. But as I said, I don't form the jet because I'm interested on the physics of the propagation, the effect in the host galaxy. So I put all my stuff, all my effort on the propagation, right? So what you will see here is the jet opening its way through this host galaxy. So what we do while it runs, I will explain what these simulations are. We discretize space. So we take a box of space. Here you see a cloud that is being destroyed by the jet, by the way. So we have a volume of the galaxy, or the galaxy and the outskirts of the galaxy. So we go into the intergalactic medium, and then what we do is to divide it in cells. We split it in cells, and then we inject the jet there. And we also discretize time. So we integrate in time with some numerical methods that are provided typically by applied mathematicians, so mathematicians who study the ways to solve the equations that we solve. And the equations that we solve are the relativistic hydrodynamics or relativistic magneto-hydrodynamics in simulations that we are running now, including magnetic fields.
Okay.
So the idea is to evolve these equations by injecting the jet and see what it does to the ambient medium. And you see, for instance, here, what it did to disrupt all the clouds, to ionize the hydrogen that was around. So the atomic hydrogen gained energy, and because of this gain of energy due to the propagation of the jet, I'll go back now to the beginning and explain the features of the jet. But due to this there's a shock wave on the front, which is you can see the shape here. So this heats up the gas in the galaxy and ionizes it, right? So this is what we do to solve the equations and to run them for the time that the simulation requires. So you see here, for instance, I will explain a bit on this. There is this is the jet itself that I recognize by the composition, and then you see here, this is a shock wave. Like I mean, imagine one of these vehicles collecting the snow, that the piling up the snow. So shocks do something similar, and they kind of wipe out all the material there. And this is a pressure increase, and I identify the shock by the sudden increase in pressure in the region. And then here, this pinkish area is region is a cloud, molecular or atomic cloud in the case of the simulations, because simulations are limited. So you cannot include everything because of two reasons: because of the resources you would need, and because you wouldn't understand anything. So we run simulations little by little, incorporating effects so we can understand them well. And the next step is relying on the previous one. So here, the step we made here was the inclusion of atoms and ionization, right? Mm-hmm. Before, all the ambient medium for us was ionized hydrogen. Mm-hmm. So there was protons and electrons, and that was it. And we idealized it that way. So numerical simulations are experiments. We cannot take this scenario and run it in a laboratory, because our laboratories don't allow us to decisize the energies, whatever. So what we astrophysicists do is to run numerical simulations as laboratories for what takes place in the universe. So, well, this cloud is completely broken. And you see how the shock wave expands and it wipes the material out, right? And this is the jet itself. So this is the channel I was talking about before. The material going through this channel runs there close to the speed of light, but the head goes to advances at a fraction of the speed of light. And this is why, if I don't have this in these images, but you would see how all the material crossing this very fast and reaching this region is filling this region here, and this would be the equivalent to the radio lobes in radio galaxies. Yeah. Here, what we are simulating is not the radio jets, but let's say the flow that would allow the radio jet to be seen, right? Mm-hmm, mm-hmm. So that's the idea.
And how long does it take to run these simulations?
Well, depending on the size, right? So it can be from days to weeks, and this is in big computers, in supercomputers, in which we use like from 1,000 to 2,000. Well, sorry, from 500 to 2,000, depending on the simulation cores. So let's say comparable to, I mean, not regular PCs now are quad cores processors, right? So we are using like 1,000 cores.
Okay.
So that's of the order of 250 PCs during days or weeks exclusively dedicated to running this, not to running the operational system, the graphic card, or whatever. They're only doing this for the whole time. So
you have to get the recipe right.
Yes. Well, sometimes we get it wrong, and that's a pity. But fortunately, it doesn't happen very often. But there is something else. It's not only running the simulation. Then you have the post processing. Then you have to analyze the results, make the movies, make the plots, and that takes long too. Actually, the outputs of these runs are gigabytes each file. So in order to, I have simulations which are like 180 gigabytes one file. And in order to analyze that, you need also a parallel program to read the files, get the numbers, go to the next file, get the numbers, and so on. And then you have to run that also in supercomputers. You cannot do that at home because when I did my PhD, I run the simulations I didn't have. There were no supercomputers, at least at our reach. And then we did it in PCs, and then we jumped into 16 cores or something like that, and that was fantastic. But now the files are so big that we need parallel programs so programs running in supercomputers, so cores running in parallel to solve this.
I see. So it was very interesting, the shape it got, I think close to the end of the movie. And it reminded me of what you said about the hose and the water and what it forms when you leave it, you point it towards the ground.
Yeah, it opens the earth, right? So that would be in 2 dimensions, right? So think of that in 3 dimensions. If you point the hose to the ground, you open a circle basically in 2 dimensions. So now the water goes in 2 dimensions. Imagine in that case the water is going to the sides and backwards, sorry, in the backward direction. So it's filling the lobes around the channel, and at the same time the shock is advancing and moving the interstellar gas, so the gas between the stars out, right? Which another interesting topic is what happens to the stars that get on the way, right? So I don't know whether we have the.
Are they getting destroyed?
No, the stars not. I have another movie. It's an old one.
It could be like a sequel for Star Wars and the destruction of Death Star.
Yes. Let me. Yeah, that would be exactly the Death Star. No, but what they do. Let me share my screen now. This would be the whole thing, right? The whole thing. Yes, desktop. That's it. If I open now this one, for instance, you see here, this is a 2D simulation, an old simulation in which we have, let's say, a core inside where there is, this is not the star. The star would be within this region. So you have a region where the stellar wind, all the stars have winds. And these winds get diluted as they propagate outwards. So you have an external layer formed by this dilute region of stellar wind. And then you have a region in which the wind is denser. So the jet is very powerful, but it's very dilute. It's extremely, so it's void, basically. So what happens when the jet coming in this direction shocks the star is that, well, would be something like this, right? So this is low resolution and so on. So the shock wave is peeling the outer layers of the wind, and this material gets embedded into the jet. And what happens is that once it reaches this region, it gets into equilibrium. So the star would be okay. If you live in a planet around such a star, you wouldn't be shocked because if you live there, you're close to the star. So, and this would happen farther away typically, but you would be burned by gamma rays. So that's the terrible point. This is the same situation but without a core. This would be for a cloud.
Okay.
Right. So if this is a cloud, and then you have the the jet is shocking the cloud, hitting it up, and it destroys it completely, right? So
like the ones we saw before that were destroyed from your simulation.
Yeah, the ones in the YouTube simulation. Yeah. Yes. Well, that was amazing, because they occupy a very small region, but when they are disrupted, they are everywhere. It's like a big burst. That was nice. Those simulations are very fresh these years, and we are still thinking about them.
That's very good, and I'm looking forward to actually using them. Yes, it's what we said, too many Zoom meetings. Yes. But they look amazing. I'll just scan through my questions to see if I have anything left for you. I know there are questions on the chat, and I will go to them very, very soon. Okay. So I will take you to 2 last questions from my side, and then I will go to the live chat. Okay. The first one, tell us a fact we do not know about the universe, something we do not know.
Well, I don't know what you know when you don't know, but I may try.
Okay, I know everything, it's true.
I may try. Okay, one thing that amazed me, and this is not related with jets, right? That amazed me some time ago was, well, I knew it because this is well known, but I thought about something related to that, and it's the following. Okay, when there are mergers of galaxies, and there are or satellite galaxies collide or have tidal effects by the main galaxy around which they orbit. So many stars are ejected outwards to the intergalactic space. So the space among galaxies is filled with stars that are there. They just escaped from these events. And I imagined once a star like that having planets and having life, and the night sky, how would it be? You may see at some distance, you may see the big galaxy, right? So like a big spot on the sky. But other than that, you would see basically nothing, because the stars are all scattered, and you don't have, well, here we already lost the Milky Way, unfortunately, but you wouldn't see the Milky Way like a stripe on the sky, and you wouldn't see many stars. You would see everything would be completely dark, and that's really terrible.
That's a bit sad. Yes.
Yeah, and I thought about that, and then the other thing I could have. Maybe I already told you now this that you didn't know, is what happened to stars that cross jets, because stars are orbiting the center of the galaxy, and then they may get into the jet. And what happens to the stars and what happens to the planets in the stars? Well, the stars survive typically, unless they have very weak winds and the jet is very powerful. In that case, well, something tremendous could happen. So the star would be peeled or whatever. But I don't think this is very probable, right? So this may be taking place in very spectacular and extraordinary cases. And about planets, the problem, because of just what I just said, because planets in which you may expect life similar to ours may be hosted, they should be close to the stars. The problem would be the gamma ray radiation, which is collimated, as I said. So all the gamma ray radiation produced at the base of the jet, where the particles are very energetic, and there are photons coming from different places of the galaxy colliding with the electrons and being re-emitted in gamma rays, all these are also collimated. So all the gamma ray radiation, basically all the gamma ray radiation being produced, goes along in the direction of the jet. And this would just wipe out any hints of life on the surface of a planet around the star orbiting close to the center of the galaxy. If you are very far away, well, you're fine.
Okay, yeah, that's a very nice thing to think of. And maybe we were lucky. If there is a jet in our galaxy, maybe we're lucky we're far away.
Well, we're lucky we're far away, because in the center of these galaxies like ours, there's lots of gamma ray bursts and supernovae. So, yes. so it's better to be away. Yeah.
Yes. Okay. And what do you think will be the next big discovery?
Well, after these years, it's difficult, right, to say something, because we have had very exciting years. Well, I don't know whether we will have something new, because we have many new stuff in the last years, but I guess something related to gravitational waves, because this is just being born and it's growing. Something related to the jet formation and very preliminary evolution around the black hole in M87 by the Event Horizon Telescope. Something like Earth-like planets. Water in Mars? I don't know. Joking.
Life in Mars.
Well, something. I don't know. But it should go in that direction. But astronomy has something really nice, and which is always surprising. And well, the better instruments we have, the less surprising it gets. But still, there is room for surprise, and you never know.
Well, I do believe that even though we might have figured out our universe now, there's still a lot to understand. Like dark matter, dark energy, if there is any other universe, how the universe started. I mean, what was before? So these are all questions that us, and also the public wonders a lot. And even though we have very advanced telescopes, and we say with SKA we will be able to observe all the radio sky and we will know everything, I think we will still have serendipitous discoveries, things that we didn't know existed.
Sure, and you will never observe everything. I mean, to the limit that you would undoubtedly know what happened. I mean, that's very well. I said never. That's too much. But with SKA at least, I don't expect we solve all the problems. Actually, related with SKA and the importance of jets. Jets might be very, very important in the evolution of the universe, because they have a very strong effects, a very strong impact in the evolution of their host galaxies, as you saw in the simulation, for instance. They wipe the gas out, and then they can reduce the formation of stars. If you don't have gas, you don't form stars, for instance. And they can play this role of equilibrating the evolution of galaxies, and maybe without jets, our universe would not be as it is, as important as that jets may be. And SKA will help us to understand that, for instance. But not everything. But not everything. I hope there must be some work for the future generations, though.
I'm sure there is a lot of work for the future generations, and
knowing everything would be boring.
Yeah, totally. Let's go to the questions from the audience. Thanks, guys, for sending your questions. So, from Philippos Economidis. Does the jets of a rotating object come out from the magnetic poles or the poles of the rotation? Do they have a preference, and why?
Okay, the point is, you have a magnetic field that reaches it's in black holes, for instance. Black holes don't have their own magnetic field, it's brought by the gas. So, and at that point you can say it's the black hole's magnetic field, but not before. And what happens is that the magnetic field arranges itself in such a way, anchors to the black hole. I'm talking about active galaxies, right? So it anchors to the black hole, and it kind of exerts a resistance to the rotation of the black hole. So the black hole must be rotating for the powerful jets to be formed, and then it extracts the energy from the black hole, right? And this can be a continuous process, as long as it may not be due to pulses, right? It may be a continuous thing as long as you're bringing material and magnetic field in. Then you have another way to form the jet, which is from the accretion disk. So depending on the angle that the lines of the magnetic field form with the accretion disk, you can have extraction of a wind that would be slower and develop along with the fast thing in the center that is formed just on top of the black hole. And the pulses maybe you refer to the X-ray binaries, to the binary stars. In that case, the whole thing depends on how the properties of the accretion disk change in time. So we know that there are configurations of the accretion disk that are inefficient to form jets. And this is more related to how thick is the disk and how does it bring the energy or liberates its energy, either by being advected to the compact object or radiated away, for instance, than to the configuration of the magnetic field. The configuration of the magnetic field is in the end basically a consequence of how the disk arranges, right? And this is why you may have pulses in binaries. Right?
Mm-hmm. Great, thank you. And then we have 3 questions / comments from, I don't know if you know this researcher, Eduardo Ros.
Oh,
hello, Eduardo. I hadn't seen.
How nice he's there.
Yeah, he's here. Excellent. So the first one says, so jets get more and more red as they travel downstream. That's the first question.
Jets, they get more and more red as they travel downstream. You mean they lose energy, or what do you mean by more red?
I don't know. This is the comment, I guess. Well, Eduardo can.
Eduardo, are you there? Can you explain?
Can you explain?
Eduardo,
and the next one.
He's an old friend and collaborator, so yeah. It's nice that he's there.
The next one is, there are jets in nature at all scales, from stars, from binary systems, from active galactic nuclei.
Yeah.
But what are the largest at all? How big? 10 times?
Yes, the biggest. That was in the quiz, in my quiz, and it's about several. Actually, Hercules A is one relatively nearby active galaxy. And if you placed it between Andromeda and our galaxy, the 2 jets would reach both galaxies. So one jet would reach Andromeda and the other one would reach us. So they are as big as intergalactic distances. Talking about millions of light years in some cases.
So Eduardo says, hi, he meant color or projected color? When he said
projected color, I don't.
So it gets red.
Sorry?
Travel downstream.
As you travel downstream, they get redder. Are you talking about core shift or?
I think it's becoming very advanced, this discussion.
No, I know. Actually, I'm sorry, Eduardo. I don't take it now. I talked about so many things that I don't know.
I think you guys should discuss in private.
No, but maybe what he says it's probably very interesting for the audience, because he does very good outreach too. I don't know. Well, if he wants, he can explain.
Yes, yes. Please explain, Eduardo. And the last one, yes, the last one was a comment. No big discoveries related to the understanding of dark matter and dark energy.
Well, now my point of view, right? In the late 19th century and beginning of the 20th century, we have ether, right? And now we have dark things. This is the limit of our understanding, right? So we know there is that there is extra mass. We know the nature of this mass. We of course have no idea. That's why we call it dark. Well, we call it dark because we don't see it. It's not shining, but it is also because we don't understand a thing about it, and only that it has a gravitational pull. So we detect it because of that. And the dark energy is even worse. So the dark energy is that's the ether nowadays. And there is a colleague of mine who retired last year. Unfortunately, he didn't get very much attention, but he has an alternative. Well, there are different, I guess, alternative theories to dark matter, but this looks really promising. And it's all about changes in time of the metrics of the universe. So keep your mind open to whatever happens. The point is there are no advances now. Yeah, there have been no advances. That's the question, the answer. And it's all about the limits of what we can do, right? What we can see and we can understand. Did Eduardo say anything?
Yes.
Okay.
So so he said if the core is blue, the jet is red, and then he was trying to tune the jets in the visible color to make a kind of extrapolation they get quite weird.
Do you mean in the simulation or?
Yes, I don't know.
In the simulation, it's about the simulation. Okay.
Yes, yes.
Well, in the simulation, the material tracing the jet was the leptonic number. Why? Because my jets are electron positron. Because in my simulations, as I said, we are introducing new physics new stuff into the simulations to get closer to real jets, right? So I injected an electron positron jet. The positron is the antiparticle of the electron. And according to jet formation theory, these particles and antiparticles are formed by collisions of photons in the very energetic photons. Energy and matter are equivalent, right? Einstein's relation. And then you, from a pair of photons, from energy, you can form a particle and its antiparticle. So around the black hole, there's such an amount of energy that you can have this. And then the jets at the base can be just electron positron. And because I am injecting the jet very close to the black hole, I assume it still to be electron positron. But the ambient medium is not electron positron, it's hydrogen, helium, whatever. Nowadays, we only have hydrogen. We will introduce helium in the future. And the tracer of the jet in that simulation was the number of electrons and positrons or leptons, what we call leptons, and in the flow, and that allowed me to check where the jet is. What happens is that when it interacts with a cloud, the cloud has protons, many protons, and then these many protons mix with the jet, and then you lose the jet flow in that following that identification pattern. And that's the reason. So it's more or less a technical stuff, but the jet was there up to the head, right?
So what happens if you have radio eyes? What do you see the jet?
If we had radio eyes, we would see what we see we would see bright stripes in galaxies if we had in the telescope, right? Because these are far away. But we wouldn't see the galaxies. We would see only the radio galaxies, which are those, at which frequency?
It's getting very complicated. Yeah. How about the jet?
No, because for instance, atomic hydrogen emits at 21 centimeters in radio, and the whole universe has atomic hydrogen. So you see where the hydrogen is due to this. This is a sudden change in the spin of the electron. If the electron starts spinning on the other direction, suddenly it loses some energy and radiates. And this traces the gas in the universe. So you see galaxies with this radiation, right? But if you go, this is like lower energy. But if you go to gigahertz, like the TVs or the radios or whatever, megahertz, gigahertz, whatever, then you would see instead of seeing the galaxies as nice spiral structures or elliptical structures, you would see nothing and then some lines.
Yes, some, as you say, stripes,
yes.
And maybe
and some
spherical regions.
We wouldn't understand anything.
Good. Well, I occupied you for a very long time.
But it was nice.
Thank you so much for the excellent discussion. You explained things very well, and I hope our viewers enjoyed this discussion. And now they're also in love with radio jets as we are.
Okay, thank you. I hope so too. I hope so. I hope that they enjoyed. And yeah, I now will go for dinner and leave you with your food. But actually, thank you very much. Yeah, cheers. Well, I don't have more, but cheers.
I was trying to keep a bit for the end because there is a quiz coming. So
thank you very much.
Thank you so much. Talk to you soon. Have a very good evening.
You too. Enjoy. Bye.
Bye.
Bye. Take care. Bye.
So guys, we will continue because we have a quiz now. Don't go. And with us, we have Paul from Bonn. Hello.
Hi, good evening.
How are you?
Fine. I have my beer ready.
Excellent. Clink.
Cheers.
Cheers. Very good to see you. It's been some time. If you remember, guys, we had Paul several times, also playing some music. So it was very nice. And Paul today will help me do the quiz. And he designed half of the quiz. So I had an idea, Paul.
Okay.
What if we ask the questions to each other and try to answer along with the audience? Because I have this problem that I never remember the answers. So maybe I will not remember and it will be fun. So, okay, this is what I'll do. Let me find, let me put the link of the quiz. Let's see, on the live chat. So guys, you can play at home. I'll just copy the link here and I'll put it on the live chat. Where is it? Excellent. And yes, okay. And then let me share my screen. I don't know if you can also see that.
Yeah.
Excellent. So this is our quiz for October. It's about jets, it's about spooky things and some weird facts, apparently. A fact that I found really interesting. So all about spooky universe, because it's a spooky month. So do you wanna, I start, and do you want to alternate? How do you want to? Okay.
All right, let's do it.
Yeah, okay.
You start, okay.
I will ask you.
Okay.
Or no, you will ask me. You ask me.
Okay. You can fit all the planets in the space between the Earth and the Moon. Is that true or false?
Okay, I will say true because I remember this one. I'm cheating. Okay.
I think it's one of your questions, but I think you're right because I remember when I'm reading this question, there is a graphic coming into my mind. I think I saw it before. Of course, you have to get Saturn's ring tilted that way, but it's mostly Jupiter. But you have all the other smaller planets, and it fits. Believe it or not, I think it fits between the Earth and the Moon. That's right.
If you orient them right, okay, good.
I think it's.
Yeah, let's see if this is. We will reveal in the end if it's correct.
Okay.
Okay, so I will ask you now: is this an astrophysical jet? True or false?
Yeah, I think so. Yes.
Okay, good. Okay, I will also. Can I send an email to myself? That would be interesting. That would be very fun.
Hey, hello to yourself.
Hello to me.
So now that's the next question for you. The largest jets emanating from galaxies are about 100 times the size of our galaxy and are the largest single objects in the universe. So you just heard the interview with our guest?
Yes, I think if I remember correctly, our guest said that this is true.
Yeah.
Yes.
That's what I heard too.
Yes, because these objects can expand to very big distances, and our galaxy is a few million light years across, so this can also extend to much higher distances.
I think we're talking about the largest single object in the universe. If we exclude galaxy superclusters or something like that.
We exclude, yes, we would not think, so when we say single object, we would not say, for example, a cluster, because a cluster is a collection of galaxies.
It's not a single object, but what about gas clouds, intergalactical gas clouds could be very large. I'm not sure if
this is also
refer these as being a single object.
I don't think so. Also, you would not would you say a filament is a single object? That's a question.
Depends on the definition.
Yes.
Thin
Because-
ice. Tricky question.
Tricky question, because a filament inside galaxies, so in interstellar spaces, is quite small. So it's not the largest object in the universe. But if you think of filaments on the cosmic web, then sure, I guess. But I don't think the idea behind this question is so complicated.
Yeah, I think if we go along with the idea of the question, we say yes, it's true.
Very nice. Let's see if we win at the end.
Okay. So the next one is for me.
Oh, the next one's for you. Okay. The length of an astrophysical jets can go up to like order of magnitude. All right. And 100 light years, 1,000 light years.
No.
100 light years.
I think it's 10 million. Yes.
10 million light years. So I'm talking. I think this question was only for one side. We heard that there are two sides of the coin.
Yeah.
But now we're talking about the one side. Okay, so
we just heard in the talk, place Hercules A, the active galaxy between our Milky Way and the Andromeda Galaxy. So we have more than 1 million light years in each direction. That's just a factor of 10 to the answer number 4, number D. So I would guess, and he said there are objects even larger than that. So I would say it's in this case it's 10 million light years. If no cats are crossing.
Very, very good, very good. Let's see. We will reveal in the end, guys. You still have to play. We're not giving out the answers.
So the next one is for you. Oh, I remember the broad discussion you had. So I think you're right. Whatever you're answering.
Yes, because so I will have to give this question as a point, either true or false, because
yes.
Yes, no.
I read it out loud anyway. Astrophysical jets can travel faster than the speed of light.
Yes. Apparently.
Apparently, yeah, that's the word that's missing here. So, so if we say it's just a relativistic trick fooling us, then the answer, of course, is yes. And I think that was the idea behind that question.
Apparently. So, Paul, astrophysical jets can be observed at X-rays, radio, and optical. True or false?
True, they can. I think, yes, most of the time, I think they're observed in radio wavelength, like we heard, but I learned tonight that the discovery photograph of such a jet was in the optical. So, and yeah, and X-ray, if there's a very high level radiation, short wavelengths, I think, yes, X-ray should be true as well. So I say, yes, it's true.
Okay. So the next one is for me.
That's one of my questions.
Yes.
Okay, here we go. So we're talking of very large baseline interferometers, and which organization is not part of the very large baseline interferometer VLBI? Is it A, the EHT, or the B, the ELT, or C, the LBA, or D, the KVB?
I'm amazed there was no more. Okay, so, all right, I will try to spell them out. So EHT is Event Horizon Telescope.
Yes.
So that is part of the VLBI.
Sure is, yes.
And this is the one that observed M87, the black hole in the center of M87. Yeah. ELT, I guess, is the extremely large telescope that will be built eventually. some point. It has a very big mirror. I don't remember now what the mirror is. When I was a PhD student, it was like a humongous size, like the design for it. I think now it's much less. LBA is the... I told you I have short-term memory. I already forgot.
Yeah. I saw it in the list. I don't know what it stands for anymore. I forgot it, but I saw it in the list.
Long baseline array.
Long baseline array, yes.
Something like that. Or maybe not. Don't take my degree away. And KVB, I don't know clue what it is. So I will say KVB.
Yes, and you know what that is?
Tell me, please.
It's a well, I'll show you the Kölsch and then you know.
Is it beer?
No. It's a Cologne local public transport system. Kölner Verkehrsbetriebe.
Oh.
It could be Köln, very basic. But it's nothing astronomical.
Nothing astronomical. Maybe
no.
we could.
It's a public transport system of Cologne.
Yeah. No.
Kölner Verkehrsbetriebe, KVB.
Okay, very nice, very nice. That is tricky because yes, I don't think many people know this.
No.
LBA for sure. Sorry, okay. I didn't know the KVB. Right. So, and if you don't know this one, guys, from home, come on, watch the movie.
Yes.
Or all of them.
Everybody should know the answer to that.
Yes, or all the movies. So the Very Large Array in the United States, which is in Socorro, by the way, was outside Socorro, in the desert, in the plateau.
Right. Yeah.
Was seen in the sci-fi movie Star Trek Nemesis, Contact, Dune, or Prometheus. Paul.
So yeah, okay. Of course, the answer, of course, is B, Contact with Jodie Foster, and it's that science fiction movie based on an idea by Carl Sagan, actually. So, and it's maybe one of the most realistic, so to say, sci-fi films, because they're based on an idea. So, what would it be like if we get into contact? So our radio bubble extends way into the local universe, into our galaxy, all the man-made TV and radio signals. And so the first thing a foreign civilization would encounter would be these radio emissions, these transmissions by humanity. And the basic idea is they take that and like bounce it back to say, hey, we got the message. So, and that's where the receiver in that movie is, of course, that array shown in the picture. Yeah.
Which is a spectacular array, and these things are really, really huge. I've been on top of one of these. So it was parked, it was looking upwards, and I have a picture somewhere on Facebook.
Okay.
At that time, when I actually climbed that array, there was no Facebook, just to say that. That was back in 2004.
Okay.
And so I went to the VLA summer school to learn about interferometric observations and how to reduce radio data as part of my PhD program. And they had parked one of the antennas for us, and we went up from the stairs. And actually, I went up on the disc. And the first thing they told me, they said, "Don't jump." I was like, well, I don't know why they would say that. I would never jump, but maybe people tried.
I remember when I did the vodcast Sternstunde. It was like an internet TV series I produced some years ago. And I had the opportunity to go in the receiver cabin of the Effelsberg 100-meter dish.
Oh, yes.
That was amazing. Well, but it was not pointing to upwards, but to the side. So you could kind of climb there. And this was an amazing sight.
Yes.
Normally,
and Effelsberg is very big. It's bigger than that dish. Yeah, so Effelsberg is 100 meters diameter, and this is 25, I think, if I remember correctly, and it's like 40 meters high, something like that.
So let's be both glad that we haven't been to the Arecibo dish when it crashed.
Well,
Okay.
shit happens.
Yeah.
Sorry.
All right. So the next question is for you, I see.
Okay, yes, I know this one.
Which EHD Event Horizon Telescope could not contribute to that first black hole image that was published of M87, the one with the first optical jet discovered, I learned tonight. And that picture was published in 2019. So which of these four did or probably could not participate?
Yes, I know the answer because I'm a geek. I'm a radio geek. I think the correct answer is the South Pole because it was not active yet.
The answer is correct, but the explanation isn't.
Ah, damn it. Why?
Okay. I did this question because I had the pleasure to attend a talk given by Professor Census, one of the masterminds behind the first black hole vicinity picture, the one we saw on every front page of magazines worldwide. And I'm an amateur observer myself, and I know the galaxy of M87 is located in the Virgo cluster. The Virgo cluster is north of the horizon, north of the celestial equator. It has a positive declination. So I know from the Rhineland, you're not able to see the Southern Cross. So vice versa, the South Pole radio telescope is not able to look at a galaxy in Virgo because it's always lower than the horizon. So they could not contribute. And that's I think
yes,
logical.
I stand corrected. Thank you very much. Okay, now is the fun part and the spooky part, and I remember none of this. So now it's your chance to shine, because I really remember none of this.
Okay.
So the Witch Broom Nebula is part of Carina Nebula, Trifid Nebula, Veil Nebula, or Flame Nebula?
I've seen it a couple of times with my own eyes in various telescopes, and it's a beautiful sight. And the answer is C. It's a Veil Nebula located in Cygnus.
Very nice. It's a very beautiful cloud, illuminated cloud.
Yeah. Of course, this is a colorful composed image. Don't expect the colors when you look through a telescope. It would be like a pale, gloomy nebula, but it's much structured when you be able to spot it from a real dark site outside light pollution areas. Yes.
Do you get this from outside of Bonn area, or is it still too bright there?
No, I've seen it close to Bonn, or we have here in the Eifel, we have a dark sky reserve, dark sky park, the National Park Eifel, and you can see it from here. But it's recommended to use a light pollution reduction filter.
Very good. This is for me.
Yes. You want me to make some spooky music?
Sure.
The Witch Head Nebula is located in the constellation of Orion, Cetus, Eridanus, or Gemini.
I have no clue. I told you I forget, and I made the quiz. Okay, so it's a a 24 chance I get this right because I do not remember. Really, I will say Orion.
And,
Don't say.
yes.
Don't say. What?
It's right. It's right.
Oh
it's
my
right.
God!
Yes. Yes. Yes.
How is this possible?
Well, the odds were with you.
Yeah. I should play the lotto.
And it's the special thing, as far as I remember, when I thought about this question, I'm hopefully remember it correctly, that this nebula is close to beta to the blue star Rigel in Orion.
Okay.
It's not easy to observe because there's a bright star nearby, but it's close to Rigel.
Okay. It's beautiful, and it's one of the selection of spooky objects. So when you Google Halloween universe, yeah it comes up. This and the rest of the collection.
If you want to use some kind of shortcut, you know the astronomy picture of the day provided by NASA and
yes.
Okay. The APOD, it's available in different languages, but the astronomy picture of the day, they have any year around Halloween, they feature a spooky nebular object. So
no, it's good, and they're very nice images, very good quality images. So this brings me to the next one, NGC 2080. The Ghost Head Nebula has a particular spooky look because it is a dark nebula, reflection nebula, supernova remnant, star-forming region. Let's look at it again.
Yes, and I think it would be tricky if you don't have the picture, but if you have a look at the picture, you can easily tell, yes, it is a star-forming region. The glooming reddish gas, of course, it's hydrogen, the gas stars are formed of, and you see these glowing eyes. These eyes are a cluster of young stars just forming inside that bubble of gas star forming region, and the spooky eyes are young bright stars that just popped up out of this cloud.
Now that I look at it, it's more spooky than I thought. Initially, I thought, it's not so spooky.
No.
Yeah. It's very spooky. It has this green gas here too. It's like, oh my God. So yes, it's stars being formed here and gas being illuminated.
Yes.
So it's my turn.
Yes. Which nebula is this? You picked it, so you should know the answer.
I know the answer. I'm so good.
I don't even remember, and I don't think it was one of my questions.
No.
Go ahead.
Damn it! We should have changed. Okay, which? Okay,
No.
No, but what?
I think I know it, but I'm not sure if I'm right.
No, but it's very easy. It's very easy.
Yeah, I think it's a ghost nebula.
Yes, you're correct. It's the ghost nebula. It looks like a ghost, right? It has this, the classic ghost you think with the.
Is there a little ghost nebula?
There is a little ghost nebula, and it's a planetary nebula. It's not circular or spherical, but yeah, it's different. And when you actually go and look up ghost nebula, they tell you, do not confuse this with a little ghost nebula. And the Skull Nebula is very spooky, but it's not that.
Yes, okay.
I think this is the last one.
Yeah, that's the last one. The
let me
Boomerang Nebula is the coldest.
No, I have to ask you. You have to ask me. Okay, you have to ask me. Yes.
Okay. Okay, the ghostly Boomerang Nebula is the coldest place in the universe. True?
Yes, apparently, because I read this. So it is true. It is true, guys. Yes, it is the coldest place in the universe, at least up to. So let me submit my questions, and I will get an email now. And I will get an email now with a notification.
If you have one or not.
Yes. So let me find this. Actually, I can also put it on.
Can I ask you why this nebula is the coldest place in the universe? What makes it so cold?
Yes, so they had this. So guys, I put this on the live chat. Okay, so that was very interesting. It's observations with ALMA that revealed this object, apparently, based on their calculations, is the coldest place in the universe. And so they say that the gas, as it flows out of the nebula, is cooling away. So in the center, you have a white dwarf star, and around it, this nebula.
Mm-hmm.
And because the gas is moving away, it cools down. And they make the analogy of how you have the refrigerator.
I see.
Working where the gas is expanding, so it loses energy, so the temperature drops. And because of that, the temperature they measure is very low, and apparently is the, so here's the value, is at minus 272 Celsius.
That's close to the absolute zero.
Yeah, so this is very, very cold. So it's colder, they say it's colder than the leftovers of the Big Bang.
It's a 3K background radiation that's always there. So it's colder than that temperature caused by the background radiation, right?
Yes, so it's a local value, and it's caused by, so it's a local minimum, let's say, and it's caused by this gas expanding and losing energy and getting cool.
Didn't know that. Great.
Yeah, me neither. So because that's another spooky fact about our universe, and it looks rather spooky. So thank you very much for playing, guys. So let me. Okay, we will reveal the results later. So, where do I have my answers? It would be nice to know the answers. Yes. So, yes, you will get this feedback on the answer sheet when I will release the results. So, this is a video that shows you how you can fit all the planets in between the moon and the Earth, if you orient them correctly. Even Pluto, apparently. I love Pluto. Pluto should be a planet. Is this an astrophysical jet? Yes, it's in the optical. This is M87. It's an optical observation of galaxy M87. And this, as we learned, was observed in 1915. So it's true. Oh, excuse me. So the largest jets emanating from galaxies are about 100 times. Yeah, that is true, as we said. The length of an astrophysical jet can be very, very big, 10 million light years. So we have objects that are called giant radio galaxies, and they expand, their jets and lobes expand at very high distances. And as we learned earlier, the environment is not very dense there, so they don't find resistance and they can grow. Astrophysical jets can travel faster than the speed of light. Well, I gave you both because I didn't put the apparent there. So from the observational point of view, if we are the observer, because of the different angles pointing towards the observer, you can get this effect where the energy
they seem to
they seem to be traveling faster than the speed of light, because imagine it like you have units of energy coming towards you, and these units are stacked one on top of the other, and it looks like it's faster. It's more energetic than it is. But it's not. It's not.
There's that Einstein speed limit.
Yeah.
Not violated.
Yes, it's very annoying, I know. So The astrophysical jets can be observed across the electromagnetic spectrum, as we found out. And this is actually an image, I think it's from, maybe I have it written here. No, but yeah, it's true. I don't remember which astrophysical object. Centaurus? No, I don't remember, sorry. But this is in the X-rays. So this is the jet in the X-rays, and these are...
Chandra?
It's Chandra, and these are also... So everything in blue is X-rays, and these are X-rays.
Yeah, it's a...
But this is the jet.
Okay.
Yes, I should have written down. Anyway. So yes, this is the funniest question ever. So yes, the one which is not part of VLBI is Cologne travel system. Still, maybe in the future, you never know.
You never know.
Never know. There's always space for collaboration. Yes, if you haven't seen Contact, watch it. And you should know that in the headquarters, so in the control room of VLA, there is an autograph by Judy Foster. Judy Foster? Yeah. It's, yeah. So that's very nice, actually. Which is the telescope? Yes, the answer is the South Pole, because it's in the south, and M87, it's in the north hemisphere. Which Broom Nebula is part of?
Veil Nebula, yes.
Excuse me, sorry, this is a bit slow. Yes, Veil Nebula. Okay, which nebula is located? The nebula is located in the constellation of... Next time I will make slides. I will be more professional. Okay. I had too much work. Orion, of course. NGC 2080. So, you know, the postcode of a Ghost Head Nebula. This is a star-forming region. See it here. Yes, it's a star-forming region. Which nebula is this?
The Ghost Nebula.
It's the Ghost Nebula, and is this the coldest? Yes, it's true. It's the coldest place in the universe. Guys, thank you very much for. I will stop sharing now and revealing all my secret tabs. Paul, thank you very much for joining.
Yes, you're welcome.
It was very enjoyable to do the quiz with someone instead of alone. I hope you guys at home had a good time. Yes, let me see if there is something on the chat. We will repeat Astronomy on Tap. So there's another event in 1 month on the 2nd Tuesday of November, which is the... You know which is the 2nd Tuesday of November? It is the 9th of November, according to my very accurate calendar. So the next event is on the 9th of November at 7 p.m. but the Central European time, because the time will change. Yes. So we will see you then.
Okay.
And until then, if you have questions, let us know on Astronomy on Tap. Thank you very much. Cheers. Have a good night, and a very huge thank you to Manel Perucho for the great discussion and explanation about astrophysical jets. Thank you, Paul.
Thank you, Eleni, for being the host.
Thanks. Cheers. Right. Good night, guys. See you later.
Bye-bye.
Ciao.